Good morning and welcome developers. For the past 10 plus years, I've had the pleasure and the honor to be leading the software and IP team at Xilinx. Now what is amazing to me is the makeup of this audience today. When I first joined Xilinx, most of our users were either RTL developers or embedded software developers. But just in the past few years, we've seen incredible demand from application developers, cloud users, and even data scientists. Now, because of this demand, Xilinx has invested tremendously in the software organization. We're doing a lot in software. The challenge for my team is to do this entire software stack, starting with RTL design flows with Vivado, going to software development flows with SDX, going all the way up to frameworks-based flows, standard frameworks such as Caffe, TensorFlow, and MXNet for data scientists. Our goal is to ensure that each one of you has a natural and productive on-ramp onto our very powerful devices. Victor talked about Versal today. Versal is super exciting for me. It is the first family of devices that has been designed from ground up for AI and software programmability. So now we can build upon this very powerful platform. I believe that Versal and ACAP is going to change the face of AI. I also do believe that we are at an incredible inflection point. Tools, IP, and silicon are coming together to make AI feasible in cloud, edge, and the endpoint. So today I'm going to give you an overview of AI, talk a little bit about some of the challenges in AI, and then talk about how Xilinx overcomes these challenges. So most of you probably know this, but AI has two distinct phases: training and inference. In training, a data scientist takes lots of data and sends them through the model. The model is fine-tuned and refined. Now, in this example, the training data set could consist of images of dogs and cats. You send it through, training is iterative, has a feedback. At the end of it, you produce results. You try and reduce errors. Errors such as detecting cats instead of dogs. Now, because training uses lots of data, lots of sample set of data, and very iterative, training performance is extremely critical. Now, latency and power is not as important in training because a lot of times training happens offline. Now, once you have the trained model, you deploy the trained model in your application, either on the cloud or the edge or the endpoint. In inference, you take small amounts of data, maybe a single image, and you send it through, and you get an inferred output. Now, performance is also very important in inference, but latency is critical. And sometimes latency is actually a constraint. A lot of these applications are in real-time systems where response times matter. In inference, power is also very important. These could be deployed in edge devices where they are battery operated. But even in the cloud, power is extremely critical because you could have many concurrent inference engines working in parallel, consuming kilowatts to megawatts of power. Now, you may already know all of this, but the key takeaway is that the requirements for training are not the same as requirements for inference. You can't take the solutions in training and then move it to inference. Well, but the world has focused mostly on training for the last few years. And the world has focused on training because we were inventing AI models, and we are inventing the applications where AI could be used. But going forward, the growth is in inference. Because all these AI models have to be deployed now in these applications, either in the cloud or on the edge. And Xilinx is focused on inference. Now let's take a look at some of the challenges associated with inference. Well, the first challenge has to do with the fact that the AI is getting innovated at a rapid pace. And keeping up with machine learning or AI is like shooting at a moving target. The second challenge has to do with the fact that we want low latency and high performance for many of the applications. The third has to do with power efficiency, not just in edge, but also in cloud. And last but not the least, and Victor talked about that, you need the whole application acceleration, not just your inference engine. You need to accelerate the entire pipeline of functions associated with machine learning. Now, let's take a closer look at some of these challenges and see how Xilinx addresses these challenges. A few years ago, most of machine learning was focused on image classification and maybe recommendation engines. But just in the past few years, there's been a tremendous growth in the universe of applications where machine learning can be used. Object detection, segmentation, speech recognition, anomaly detection are just some of the applications where machine learning is being used. And there are many, many, many more. The universe of these applications is growing at a tremendous pace. Now, if you just look at any one of these, there's a lot of innovation going on in AI models also. Every day there are new models being created to be used in any one of these applications. Now, if we take a look at just one of them, classification, image classification. Now, image classification has been around for 30 years. But AlexNet came out in 2012, and since then, in the past 6 years, there has been a tremendous growth in the number of models being created. There has been an explosion. For the first few years in this period, the focus was on improving accuracy. But you can see lately, you can look at the example of MobileNet, the focus is on improving the efficiency of the AI model. The reason they are focused on efficiency of the AI model is because this AI model can now be deployed in mobile devices. Now let's take a look at the structure of these AI models. Well, if you look at the structure of these AI models, they started with very simple feed-forward networks where convolutional layers talk to the next layer. Very simple AlexNet. Now we moved on to more complex networks where there are many convergences and divergences, such as GoogleNet. Moving on to even more complex networks, there are convergences, divergences, but there are also bypasses. This is DenseNet. Now there's also research today going on with respect to doing some of this work through shifters, not even using matrix convolutions. To me, if you look at these networks, look at these models, there's really no commonality between these networks other than the fact that there is some linear algebra going on in the background. They are very diverse. Not a lot of commonality, and the diversity will only increase. Now you overlay this with the fact that there is research going on and there's deployment of low precision arithmetic. We started in 2012 with floating point 32. We are now at integer 8 arithmetic, moving to binary networks potentially by year 2020. Now the reason is very simple. If you look at the energy consumed by floating point 32-bit adds, it is 30x compared to integer 8 add. And that's why people are moving towards lower precision arithmetic. Now, with all this innovation in AI, imagine, if you will, you're creating a fixed function chip, fixed architecture ASIC, to accelerate one of these inference engines. You start off with a spec on your most state-of-the-art model, After a few years, you get the silicon back, the state of the art has changed. Now your silicon is optimized for a network that is not state of the art anymore. Fixed silicon architectures are not the answer. Answer is adaptable hardware. Adaptable hardwares such as Xilinx FPGAs and ACAB allow you to customize your data flow. They customize your data flow towards your current state-of-the-art network. They allow you to customize your memory hierarchy. You can try and increase the amount of on-chip memory used instead of going to DDR. You can customize even the precision. You can even have mixed precision. And you can do all of this, and as the state-of-the-art changes, you can re-implement all of this without a silicon rev. Now, Xilinx and others have created something called domain-specific architectures. Victor talked about it. DSAs, domain-specific architectures. These can be created and tuned for a class of networks. Tuned for a class of the current state-of-the-art networks. And these optimize across these vectors. Custom data flow, custom memory hierarchy, and custom precision. You can customize all of this to improve your latency, improve your power, improve your cost, improve your efficiency. Now, one such pioneer in creating DSAs has been DeFi. DeFi has unique pruning technology that allows you to customize the data flow. They can customize the data flow for the networks in question. They can even quantize your network, tune in the precision. You can retrain and get the accuracy back. Their technology was so unique, we started working with them about 2 years ago. We partnered with them. Fantastic partnership, great technology, and now Xilinx has acquired DeFi. So all of DeFi technology is now available to all our users. Now this is an example of a DSA that DeFi has created. This is focused on speech recognition, tuned towards LSTM networks, long short-term memory. They made sure that they customize the memory hierarchy using sparse matrix computation. So you can improve power as well as cost. And look at the precision. 12-bit weights, 16-bit activation. No fixed function chip would go for something like that. Right? Tuned in the precision to improve your latency, improve your power, improve your cost. Now here's another DSA that we created. I think Victor talked about it, XDNN. This was focused on a class of feed-forward image classification networks, networks such as YOLO, ResNet, GoogleNet. We also customized the memory hierarchy here, where we added buffering between layers of convolutional layers so that we don't have to go to DDR again. Reduce the times we go to DDR to improve, again, latency, improve power. We did integer 8. Now, by itself, it was interesting. We got pretty good performance. But we actually found more innovations, more algorithmic improvements that we could do on XDNN. And within 6 to 9 months, we improved it further. And Victor talked about it. We improved the latency and got to a third of the latency that we had in a previous version. And we improved the throughput to almost 2x, and we re-implemented the whole thing, again, on the same silicon, no silicon rev required. You can continue to innovate on your networks. You can continue to create these DSAs. You can tune your DSAs to your network, re-implement it, no silicon rev required. So we talked about latency. Now let me explain why latency is important. Let's say you're driving a car, or rather, the car is driving you. In your autonomous car, you have an inference engine. The inference engine is watching all the hazards, and as the hazard approaches, the inference engine will try and stop the car. The faster the inference engine reacts, the better the latency, the lower the latency, the shorter the stopping distance. And the chances of you avoiding the hazard go up. So latency is, of course, very important. Low latency is very important. But you may be driving very fast. Therefore, frames per second is also important. Throughput is also very important. So throughput and latency is important. Low latency is important. So let's look at how GPUs and CPUs handle throughput. Let's see how they optimize throughput and contrast it with how FPGAs and ACAPs optimize throughput. So with GPUs and CPUs, you have to load in sets of data. They call this technique batching. Load in inputs together. At this point, you load in the model weights. Now you compute your results and outcome results together. Now, the reason you have to load in model weights together to compute at the same time multiple results is because memory is a bottleneck in these instances, and you don't want to be loading weights again and again. Now, because you do this type of batching, you can get either high throughput or low latency, but not both at the same time. Well, let's look at how FPGAs handle throughput. Well, FPGAs, you can actually pipeline the input, get the results out. Pipeline it, get the results out. You don't have to wait for all the inputs to be loaded together. So you get low latency. Now, the way FPGAs and ACAPs would handle throughput is by customizing again the data flow, customizing the precision, customizing the memory hierarchy. So what you get here is high throughput and low latency. Let me show you a benchmark example to illustrate this point. High throughput, low latency. This is a Versal device benchmarked against GPUs and CPUs. In this scenario, there is no latency constraint. No latency constraint. The Versal device would be 2x better than GPU and 43x better than a CPU if you use GoogleNet as your benchmark. Throughput, images per second. No peak teraop numbers here. Real numbers. You get 2x better than GPUs, 43x better than CPUs. Now let me tune in a latency constraint. Sub 7 milliseconds. At this point, Versal, interestingly, remains constant with respect to throughput. But GPUs has dropped, and now Versal is 2.5x better than a GPU, and Versal is 72x compared to a CPU. Let me tune in the constraint even more. I tighten it to sub 2 milliseconds. Extremely valid constraint for many of the applications. Now Versal is 8x better than the GPU. Well, and the CPU has dropped off the chart because it can't satisfy this constraint. Let me show you benchmark results with more GPUs and our current Alveo board and the Versal device. You can see Alveo gets about 4,000 images per second with a constraint of 2 milliseconds, and Versal gets about 22,500 images per second using GoogleNet. Significantly better than all the GPUs, even with our current board that we launched today. But that's not all. If I use D-Phi's pruning technology, it goes better. Alveo gets to 5,300 images per second, and Versal almost touches 30,000 images per second. DeFi can give you 1.3x to 8x better performance depending on the network you use. So we talked about latency. Let's talk about power. Now, it may be obvious that power is important for edge and endpoint devices, but it's also very critical for cloud. And I'm going to show that with an example from one of our customers here in the audience today. This is SK Telecom's personal assistant device. This is the device they sell in South Korea, and it's the most popular personal assistant device in South Korea. Like Alexa, this will send data up to the cloud, and SK Telecom will do automatic speech recognition. Now, SK Telecom has seen some tremendous growth with this device. Just in the last 2 years, they've gone from 0 active users to 4 million active users. And they expect that they would have to handle about 1 billion conversations every month. So naturally, they were looking for some acceleration. Now, they started doing benchmarks against GPUs, FPGAs against GPUs, and they saw that FPGAs gave them 5x better performance and latency, low latency compared to GPUs. But interestingly, they got 16x better performance per watt compared to GPUs. So they did their own DSA, optimized for their speech recognition, deployed it. The performance per watt advantage that they got translated directly into total cost of ownership because there are many, many inference engines running in the cloud at the same time. Now, SK Telecom, as I said, is in the audience. They have a talk today in the afternoon. So anybody wants to understand how they did it, they should attend this talk from SK Telecom. So yet another consideration has to do with the fact that inference engines don't work in isolation. They have pre-processing and post-processing functions that go along with inference engines, and Victor talked about whole application acceleration. You need to accelerate the entire pipeline of functions to get your required latency. Now, I'm going to illustrate that with a real example, again from a customer. This is in the smart city space. As you know, smart cities are popping up everywhere. In smart cities, there are networks of cameras that are deployed to avoid threats. By some accounts, there will be about 1 billion cameras that will be installed on government sites and commercial buildings by the year 2020. Lots of data. Now, whether you're identifying a criminal from a crowd or identifying a stolen vehicle using license plate recognition, AI is playing a huge role in all smart city applications. Now, what I show here is the back-end engine of a smart city camera deployed in the cloud. Now here, the application has been split between CPU and an accelerator. Now in this scenario, the accelerator happens to be a GPU, which can only accelerate CNN function or your image classification function. And at this point, you get about 82 milliseconds of latency, 75 watts of power. Now, if you redo this application in an FPGA, you can move some of the functions that were surrounding these inference engines into the FPGA again. The motion analysis function was moved to FPGAs, and now you get 26.1 milliseconds of latency, 50 watts of power, and the throughput also improved 3x. It went from 12 frames per second to 38 frames per second. Again, whole application acceleration, not just the inference engine. Okay, so we talked about the importance of agility. We talked about low latency and high performance. We talked about power efficiency. We talked about whole application acceleration. But what is also, or just as important, is getting you to implement, the developers, to implement your AI function in your applications. And my team has been focused on creating the entire solution stack, the machine learning solution stack, to make your job easier. And this is a solution stack that we have developed. This is what we've assembled. The components come from us, from our partners, or some come from the AI community overall. Let's start from the top. We now have support for standard frameworks, Caffe, TensorFlow, MXNet, that allow a data scientist to create custom models. But you could create custom models, or you could use some of the models that we have created. These are pre-trained, pre-optimized models that can be deployed in your application. And we deploy them in a library that the industry calls Model Zoo. We also have accelerated libraries. These are library functions that go around inference engines that allow you to do whole application acceleration. Functions such as OpenCV in the vision space. We have pruning and compression technology that allows you to customize your data flow. We have quantization and compiler tools that allow you to customize the precision, do the retraining, and then deploy your network with no loss of accuracy. We have runtime libraries that allow your AI application to talk to the external CPU host, the x86 host, or the processing subsystem within our device. We have DSAs. You can write your own DSA for your specific application, but we have our DSAs ready to be deployed. XDNN, Descartes for speech recognition, Aristotle, this is a DSA for image classification for the edge-based devices. And this all sits on top of FPGAs, either in the cloud using Amazon F1 instance or Alibaba FPGA as a service, Huawei, Nimbix, and so on. Or they can be deployed on our Alveo boards, the ones that we launched today, or they can be deployed on custom boards that you create. We are very focused on AI and making sure that all application developers have an easy route to creating their AI applications. We are continuing to add more and more to the accelerated libraries, improving the quantization tools, compiler tools, adding to the model zoo, and so on. We'll continue to invest heavily in this space. Artificial intelligence revolution is here. There are many opportunities in inference. There are some challenges as well. We believe that our adaptable hardware is the best alternative to implement your AI application in cloud, edge, or endpoint. Because we allow you to match the speed of AI innovation and not be constrained by silicon design cycles. We get you the best low latency and highest performance for many of the applications many of the demands of applications. We get you the best power efficiency, not just for edge, but also for cloud. But last but not the least, we allow you to do whole application acceleration. As I said in my opening remarks, we are at an inflection point. Tools, silicon, and IP are coming together to make your AI application feasible in the cloud or at the edge. Whether you are an AI expert or if you're starting AI for the first time, trying to understand how to deploy your machine learning AI application, we look forward to working with you on your next project. Thank you.